Hello, everyone, and welcome to Ask Daron. Today's topic is the key differences between single and twin screw technology. This webinar is designed to be as interactive as possible, so we encourage you to ask your questions throughout this 30-minute session. My name is Christian Davis, and I'll be your moderator for today's event. With locations around the world, CPM is a leading global supplier of twin screw extruders, extrusion systems, high-performance replacement parts, ring extruders, thermal equipment, and supporting services. Answering your questions today is Daron Fraim. Daron has over 20 years of manufacturing experience in various industries, including thermoplastics. More than a decade of his work has been directly related to extrusion compounding using co-rotating twin screw extrusion technology. At CPM, Daron works closely with our customers to support their application needs with respect to machine configuration, screw configuration, technical training, and other process improvement initiatives. Daron, I'll now turn it over to you.
All right, thanks, Christian. Welcome, everyone. It's good to see, I can actually see the names of attendees at the moment. So what I'll do, since this is our kind of our first attempt at doing more of a live session and Q&A, let me just pop my presentation just to show this first slide to get things kind of kicked off. What you'll see here, this is just to kind of understand where the single screw typically fits in the picture of things in terms of the plastic supply chain, where you'll typically find a single screw versus twin screw, kind of their sole purpose, their role in the essence of the supply chain. So when we look back upstream, when we talk about precursors, or you'll hear the term feedstocks or monomers, that's your starting materials that's of course extracted and fractionized off of crude oil processing, so like ethylene, propylene. And then downstream of that, your polymer producers or resin manufacturers, your big players like Lyondell, BASF, Dow, Ineos, Westlake. Basically, that step is to build the polymer. So they take the precursors and they polymerize PE, PP, just a couple examples here, or polyaddition polymers. They'll make different grades, of course. Injection molded grades typically are higher melt flow grades for fast injection. Extrusion grade is lower melt grades for the purpose of higher melt strength. A lot of those applications are stretching type applications, so you need stronger melts. But then one step past that is kind of where the field of where the twin presents itself in terms of material development. So anything, when you think of plastic components, anything you touch or see made of plastic normally has the resin plus additives, and there's a variety of reasons we put additives. Here you'll just see some quick examples, economizers like calcium carbonate, a lot of mineral fillers. That's to cheapen the plastic essentially without really creating any negative properties. Those mineral fillers are pennies on the pounds versus dollar plus per pound typically on resins. And they do offer some beneficiary properties, like they'll add some stiffness to the polymer. They'll help prevent like voids or sink marks in molded parts. Also for injection molding, as many of you know, your cooling cycle is usually your bottleneck in the process. So the presence of these mineral fillers help increase thermal conductivity. So they'll allow the molded part to cool faster. And then like processing aids, usually those are added during processing for the polymer to just preserve the properties. So antioxidants, thermal stabilizers, lubricants, and plasticizing agents, things like that. And then your functional adds are normally to enhance the property. So if you're trying to add mechanical strength, reinforcement types, anything outdoor needs UV protection, your electronic type components usually have to meet certain flammability ratings, so flame retardants, things like that. And that's what the twin essentially is. Its dominant player is its mixing capability to really melt and mix these diverse formulations. Now, downstream of that is your finished part producer, your converters is what we call them. And that's where the single screw is most dominant. Essentially, it's like a melt pump, and so it serves very well at just remelting the material and pushing it into a die mode to form the part. So with that, just to kind of understand a little more where they fit across the landscape, I'll kind of open that up. If there's any direct questions, I do have additional material, but I figured since this is more of a live session, if there's any direct questions in comparison to the two technologies, advantages, disadvantages, or whatever. So I'll leave it up to you guys to start asking questions.
Hey, David, last time we did have it on presenter view when you were showing, so we'll need it on the full screen. But I was thinking maybe you could tell us, the biggest difference, your go-to. What's the biggest difference between the single and the twin?
Yeah. No doubt. That's the main difference, as many of you know, between twin screw and single screw. One big takeaway is there's one screw is the difference. So one machine has two screws, the other one has one. So 2 minus 1 is one screw. So that's kind of our inside joke. I tend to present that even at the Polymer Center to kind of open it up, set the mood, set the tone. So I can't see anyone really laughing, but that's kind of our kickoff, the obvious difference. But anything beyond that, you guys have any? I don't want to dominate. In most previous webinars, I spend probably 50 minutes on material. And a lot of times we try to field questions toward the end, and there's very limited time. So we only get 2 or 3 questions coming in, and then we cut things off. So this is more of an opportunity. So open discussion to give you some time and opportunity to ask any questions you might have. I don't know if many of you out there work with both twins and single, even in the field of compounding, but I'll allow a little bit of time here I know these questions are being typed in, so. All right, we got someone typing, so so any key things to keep in mind if you're moving an extrudate between single and twin. So that's from Mike. When you say moving an extrudate between single and twins, are you talking taking a compounded material from a single to a twin, or vice versa? One thing I'm not clear is are you say you're trying to go from single to twin or in reverse? And is this a compounded application where so which chemistries would you recommend to run on twin screws is another question over single screws in powder coatings. One thing to note, the one thing that is very dominant on the twin is the capability to mix. And so that's one thing that the single is very limited, is its capability to really mix diverse or very complex chemistries or additives. I have worked personally with a single screw in compounding, and it has some capability of mixing, but it's very limited. Typically, it's very simple formulations recommended. And so normally the sections on a single screw are very limited. And let me just present right quick. I've got this so we can see this. I think a visual serves much So when we look at a mixing in a single screw, now this is typically on what I call simple formulation compounding on a single. You can see here, these are very small sections typically. Most of them tend to be toward the end of the shaft. Some of them are centric to the machine, but you can see they're very short mixing sections. And so there's some that are trying to split the melt for elongational or distributive. Some offer dispersive, like this one here on the very right with the blue arrows. This one is a dispersive because it's an open, closed, alternating fluted type section. So the melt enters the open channel, but here it's closed on the end, so it can't go anywhere. It's forced over this barrier between this other channel. You can see this channel is closed here, but it's open-ended. So it's alternating open on this side, closed here, and then it's closed here and open. So the melt goes in here, crosses over. When it crosses this barrier is when it's dispersed. Now you can see some of these others. There's distributive here. These are split flight, so it's allowing crossover mixing in these channels. But you can see here, there are specialty designs. They're very short sections. They can cause stagnation and surging, but they're very limited length. So typically you won't see a very complex formulation utilized on a single. Where a twin, you have you have such a diverse geometry of elements and types of mixing. So hopefully that answered. I know the one question was on powder coatings. Powder coatings usually have quite a few components. Normally what I see for most powder coating applications are twins used. So let me move to the next one. My understanding is that twin screw has better venting capabilities to remove oligomers. Yes, would there be any ideas to improve venting and to remove fumes oligomers? So let me go back here, jump back a little bit here. We get into devol. So on a single screw, in order to devolatilize, you have to have what's called a two-stage screw, and you can see here if you look at this, and if you're familiar with single on how it works and it melts is via compression. So you can imagine the barrel wall, and I can show that in another picture. But the material's compressed because you're getting reduction in clearance here. As you can see, this channel's deeper here in the feed, but it reduces as you go here. That's the first compression stage. And then you have what's called a decompression. So you go back to your flight or your height or clearance as you were in the feed section. So this is where you typically will see devol, a short section here, and then you got what's called a second stage compression. That section, the challenge with a single screw is it's hard to control degree of fill because screw speed and feed rate are dependent on one another, where that's the opposite in the twin. When you think of turning that screw faster, you're feeding more material in the machine. So if you're really pushing the limits of that single screw and its capability on throughput, it's hard to control degree of fill because you can't speed the screw up without, conveying more material forward, where in a twin you can. So I have personally worked with a single screw with a vent. Normally this decompression is about centric to the machine, but I will tell you from experience, we always seem to experience vent flow. The challenge here too on a single is you got to think of how much volatile content you're dealing with. If you're dealing with a high moisture level or volatile, then your vapor velocity becomes an issue in one single short stage vent. Where in a twin, you can have multiple vents, so you can handle larger amounts of volatile content. So hopefully that kind of answers some of that. So back to Mike says, any ways to modify the single to improve its mixing? Okay, so really not so much, Mike, because it's a fixed screw typically. So you can see here, it's, you can buy these different screws. I don't know what length of machine you're working with. The one I've worked with was a 40L over D, pretty long machine for a single, because most conversion applications they range from typically 20, 24 to about 32L over D. But it will depend on the machine manufacturer, the screw, but very, very limited on the single screw for mixing, unfortunately. That's probably the key thing that is the most dominant with the twin, is its mixing capability. And I'll just show here, since we're talking about mixing, you can see here in the twin screw, there's a diverse geometry of all kinds of elements. So if you look here on these first 4 elements, these are distributive type mixing elements. These are gear type. The first being what's called the TME, or turbine mixing. It's got like, teeth, and then so it splits the melt stream multiple times over into like spaghetti strands. So you get a real high surface area. They're very good for glass without shearing or damaging the fiber. They're very good incorporating liquids. Same thing on the ZME. Same thing, geared teeth, but they have an angle at the way they're staggered. This one here is an SME screw mate. It's almost like a standard conveying element, but it has notches cut out of the flight, so to allow cross over mixing from channel to channel. This is an Eagle, similar to this, except it's not notched in multiple locations. On the very edge here, it's got a small leakage where this channel can cross over into this channel. These are your standard kneading blocks. Different stagger angles, different number of lobes. They offer them in different the lobe width or length of the element. So you have narrow type, you have kind of an intermediate, and you have larger, longer. But the fact that you can place these along the process length in multiple locations, you can sequence them, different configurations, different lengths. This is what really is the dominant player on facilitating mixing. So let me see any more questions. So we've addressed powder coatings, we've addressed the venting, we've addressed mixing. I'll hesitate a minute. If there's not any more questions, I'll go through the slide. We've got about 12 minutes. So I'll just let me tap back in on the presentation. And then if there's additional questions, I'll certainly address them. So we talked about this. Let me go back to presentation mode.
Daron, we're going to want sorry to cut you off. We're going to want the other mode for viewing.
Okay, sorry. There we go.
There you go.
So this I touched on, as I mentioned in the very opening, where the twin normally lands. So if we look side by side and we talk about feed method, so the single screws flood fed, twin screws start fed. Material conveyance, the single screw uses drag flow, twin uses what's called positive conveyance, and we'll see a little more about that. Melting mechanism, normally the single screws classify as what's called viscous dissipation via compression, and we'll see that a little more in the next slide. Conduction plus shear, they both will have barrel heating conduction. But in the sense of the twin, utilizes the kneading blocks for more of what we call a shear input. Overall design on the single is very slight modularity. And when I say that, meaning there is independent barrel zone heating, and then you do have some variation in your screw, with some screws being general purpose. Typically on injection molding machine, they use a general purpose screw, which is nothing fancy. It doesn't have any mixing. Some injection mold screws at the end will have a little bit of mixing on the tip. And then we saw in the previous slide a little bit of variations on some of the options on the screw in terms of mixing toward the end or centric. Very, very limited, very small sections, but again, the twin is very excellent modularity. I mean, a lot of diverse geometries, placed them along the process length and so forth. Mixing, as we talked about, very low capability. Twin is very high. Devol, very limited with the two-stage screws, very short section. You can't control degree of fill as well. Where on the twin, you do have that capability with multiple venting, can control screw speed, feed rate independent. So you can feed at a certain rate and turn your screw up and really reduce low fill in that machine. The only advantage the single screw really has over the twin is its pressure development. Because of the drag flow, it is considered like a melt pump, so it can really pump material. It's not uncommon to see pressures, 2,000 to 5,000 psi, depending on the die restriction, whether it's thin film or so forth. Where the twin struggles, it's not a very efficient pump. So I touched on this. I won't really go in this whole lot, just to say primarily the single is found as a melt pump in conversion processes to pump the melt into a mold or die. So here's just some examples: injection molding, extrusion sheet and film, extrusion blow molding profiles. So when we talk about the single screw feeding and conveyance, as I mentioned, single screws are flood fed. So you're fully filling that feed section and then conveyance via drag flow. The key difference here to understand is that the single screw has to utilize the barrel and the screw to move the material. So it has to be filled. And that's where your disadvantage of devolatilization, that's your disadvantage of trying to feed anything downstream. When you think about feeding components downstream, like many of you may side feed, liquid inject. Now you can on a two-stage single, and we did this as well. In that decompression zone, you can typically liquid inject, but feeding a solid there usually is very difficult. So you're very limited. Everything has to be fed in the feed throat for the most part. We're a twin. You can see here has two screws, obviously, and that's where how it moves material. It's transfer of material from shaft to shaft. So it doesn't have to utilize the barrel wall, so it can run at a low degree of fill. So now it favors feeding materials downstream in low filled areas, devol with low degree of fill. Here we talked about the viscous dissipation, and I'm talking about compression ratio. This is a single, so you can see in the feed section, you have the deeper channel, and then as you go down the screw, you see a reduction in clearance between the barrel wall. So you can see how filled this machine, and it needs to remain filled so it has contact between screw and barrel wall to drag flow the material. And what happens is you start forming this melt film, and as it generates heat, that viscous dissipation will eventually melt the solids. Typical compressions 2 to 3. Higher melt flow grades, you need a higher compression because they don't generate as much. They're lower viscosity and don't generate as much frictional heat, so you need a higher compression. But you can see here viscous dissipation, the melt film. This just shows as it progresses how it breaks up the solids, and basically the melt pool starts growing. Again, modularity we touched on. Single screw does have independent barrel heating. Now this screw here, if you notice, this is more what we'd call a general purpose. There's no mixing section. It's a single stage screw, just has compression across it. But the twin, obviously, as you kind of can see here, we can configure these shafts in multiple ways in terms of how much mixing, type of mixing, what length. We can put multiple vents. So the modularity is so much greater on the twin. That's why it's favorable on mixing, devol, and you can control melt temperature better because you can configure that screw with, what I would call more gentle type mixing or more aggressive, depending on your polymer type and additives and amount of additives and so forth. Like I said, you don't have control of screw speed and feed rate. It means if I slow this screw down on a single, then I slow the intake of material. I can't independently control my feed and screw speed. Where on a twin, I can dial in a specific feed rate and I can adjust that screw faster for low degree of fill, or I can slow it down with a higher degree of fill. Again, we touched on this in the mixing section of the single. There are some capabilities, typically simple formulations. The one application I've worked with where you'll see a single screw on compound, it's pretty common to do what's called polymer alloying or mixing different grades. We would use a single screw to bring in like one melt grade of a TPU and a different. A lot of times they want to melt different or combine and melt different melt grades to kind of find a happy medium on properties. I have used a single screw where we incorporated like a PE wax as a lubricant, internal lubricant mixed in with a polymer. You will also see a single screw where you disperse color. Of course, like injection molding machines, if they're going to add color to their finished part, they'll bring the parent polymer in and then they'll dose in their color master batch pellet, usually like 2 to 4% range on the color. So they do have some mixing, but it's extremely limited. You know, 2-component type systems. Again, we touched on it. Oh, sorry.
Darren, it looks like we got a few questions that came in. I know we're getting tight on time if you want to check those out.
Yeah, let me check. Okay, so when do you apply cooling of the screw at the single screw extruders? Okay, so that one, yeah, is really dependent on the application. PVC is pretty common. If you have very thermally sensitive polymers, they will incorporate internal screw cooling. So to answer that, just really dependent on the polymer, how thermally stable it is. So then we got a question, can you not slow the screw speed and add more barrel temp to provide more melt temp? Yeah, I mean, you can, depend on that machine size. And I assume that's in reference to a single. Can you not slow the screw speed and add more barrel temp to provide more melt temp? That may have a slight influence. Typically, it's the shear heating is your more dominant. Usually 80% of your energy, or 70 to 80, typically we say, is imparted in the actual shearing from the screw. Because the single is filled more, you can have some conductive influence, but again, it's dependent on what size of that machine you're running. But it will have some influence, particularly in your once you get past the melt section in that machine. And scaling from single to a twin, are there any general recommendations or relationship? Yeah, scaling. In terms of scaling, yeah, normally the recommendation is to stick with the SEI or SME, your specific energy input, particularly if you're getting good properties on your single and you're trying to match that to a twin. Ideally, we recommend trying to follow that same specific mechanical energy input. That's your key indicator of how much energy is imparted into the actual material itself. So, yeah, and yes, the question in terms of the SCI or SME, yeah, the same. You want to calculate how much, so your screw speed and basically your torque level, you would use that same type calculation. Only difference when you took it total energy input, there may be more conductive from the barrel heating. So when you think of SME versus temperature from the barrel heating as well. But yeah, mechanical energy, I would just caution on scaling that there could be differences in conductive influence from barrel heating. Again, these are dependent on the machine sizes. So ideally in those situations, we recommend trying to run adiabatically where you limit the amount of barrel heating. So you're really focusing on the energy input from the screw. So we have one more question coming in. And one question was, will the presentation? Yeah, Christian, how on sharing this presentation?
Yeah, this will be available on 1cpm.com within the next week or so. And we will also be doing the session again today at
Yep.
12 p.m. Eastern Standard Time. And you can also email Daron directly at daron.fraim@cpm.net if you'd like to keep your conversation going.
Yeah, certainly. You have my contact.
All right, well, thank you, Daron, and everyone else that joined us today. Like we mentioned, a recording of this webinar will be available on 1cpm.com within the next week or two, where you can also find all of our previous editions as well. If you have any more questions or didn't get yours answered today, you can email Daron directly at daron.frame@cpm.net. Thank you, everyone.